is grabbing the inventory and grabbing baseline data. So that SPV script is going to grab SAR data, PCP data, it's going to grab accounting data, whatever it can find on the system. And then I'll tar up the directory and pull it back. Okay. Now this next chapter, I intend to remove a lot of the slides in it. For time reasons more than anything. When I first put out this course, the Origin 2000 was brand new and we had to talk about hypercube topologies and stuff. But for time reasons, I'm going to skim through a lot of this chapter. Okay? There is another bullet on my home webpage for IFO, IRIX functional overview, that has a lot of description to match these slides. But basically, I got to figure out what do I have for a hardware configuration. I have to know the capacity. Capacity is how much do I have, how many CPUs. A 16 CPU system, that's the capacity. And then bandwidth being how fast is it. So basically, again, when I look at a system, there's something called queuing theory, and queuing theory says treat each of these resources as a separate service center or entity. So if I go to the bank, there are 5 different lines, and each line has a different quality of service expectation. There's going to be one line for commercial banking, and you're going to expect people to be waiting long in that line because they're off counting money bags or something like that. So whenever I go through a system, as we said before, I always do the same drill. I look at CPU first, I look at memory second, I look at disk third. Most people look at that in that order because of pricing. Now memory has gotten a little bit more expensive than CPUs, but what good's a system without CPUs? So most people still look at CPU first because that used to be the most expensive item, but maybe or maybe not these days. But I still need to see CPU utilization first, then memory, then disk, then file system buffer cache, then your inter-process communication, and finally your networks. So that's 6 resources. Okay. And I'm not paying attention to networks in this class, and very, very little topics on IPC, but we've addressed a little bit of it today already. I'm mostly interested in the first 4 resources with this class because of time reasons. So with each one of these resources, I want to look at how busy it is, or utilization. I want to know queue length, how many things are trying to use the resource. I want to know my wait times, and I want to know my service times for each of these 6 resources. Okay? So for the first one, for CPU, I'm just going to use SAR -U and also -Q. -U will give me my utilization, -Q will give me my queue lengths. For memory, I want to use SAR-big R and SAR-little w. For disk, it's SAR-D. For buffer cache, it's SAR-B, but I also prefer to use the command buffview. For IPC, it was the IPCS-A option. And for networks, we're not going to address it, but there's a whole bunch of commands to look at your network areas. PCP, for example, has a whole bunch of network statistics that SAR does not have. So generally with networks, I'm looking at PCP. So that's all I'm trying to say. Every time I got a system, I got 6 things that a program could be waiting on. And I want to know how busy are they, how many things are trying to use them, and how long does it take to use them, how long do I wait to use them. Those are my 4 key metrics. Okay. Now in this example, I've just pointed out that the R10K is the CPU. R10K, 12K, and 14K have what are called hardware counters. Pentium chips also have hardware counters. So if I'm 100% busy on my CPU, the hardware counters tell me what is my CPU doing. Am I branching? Am I loading memory? Am I doing floating point computation? Okay. So we're going to look at these hardware counters coming up tomorrow afternoon. Memory, just leaving alone. right now, and then for I/O, secondary cache really doesn't belong in that. You should just take that out. Secondary cache is not involved in the I/O path. But then I do have the other types of resources that I talked about. My buffer cache, my inter-process communication, application buffers we're going to talk about later, and then my peripherals, direct attached SCSI or fiber channel, and various other channels that may have peripherals attached to them as well. So beyond those 6, the 7th one would be miscellaneous, which would be things like a CD tower, tape, various other miscellaneous peripherals. Okay, and if I were a petroleum site, tape would be of interest to me, but most other sites don't care about tape. So just think of that. Whenever I get a system, I want to know how much I've got, and then I want to run through these 6 resources and figure out how much is there and how much is it being used. I want to know how busy it is, how many things are trying to use it, and what my service and wait times are like.
Now those commands like SAR minus U minus Q is going to give you the percentage of how much is busy?
There are different numbers. The U option will say what percentage when I look at the system is it busy. And the Q option will just say how many things are on the queue.
Okay. Oh,
and we're going to start looking at these numbers first thing in the morning.
Okay.
Okay, and we'll look at different systems. So when I go to that SPV command, it's going to go through it in that order. So SPV is designed to go left to right, top down, as I drill down into my data. Okay, so I start off with SAR, then I go to accounting, and then I go into specific tools like PAR.
Now, when you want that information from SAR, you want that to be historical or?
Historical. I want my baseline first. If I'm logged in the system live and I'm experiencing an event, then I will go to live SAR. Okay, we'll talk about that, but that's what the check config SAR on did, was give me historical. Otherwise, I could only get live data. But the live data is only, that's relevant in every situation.
Exactly.
So you've got to be able to decide what's important to me. So for example, I could care less if code 2 is my bread and butter. I could care less what the I/O metrics tell me, because code 2 does no I/O. If I'm on a mail server or news server, I/O is critical and it's lots of little files. So once I understand the programs that I'm running and what their characteristics are, that gives me an idea of what to look for. It's like a puzzle and I'm putting all these different pieces together. Okay? So we're going to go through that process here. But even looking at the data can be completely different from one site to the next. They could be running the same application set and still have different data associated with it. I'm just going to get rid of that.
Change something just a little bit.
Go ahead.
In here on processing comparisons, I notice this book shows the R10K is 390 peak megaflops.
Yeah, that's old, but
The old, when I went through the R10K engineering course when it first came out, and they quoted right at 600 megaflops.
yeah.
Right. So which one's right?
That's why I'm getting rid of this chapter, because this stuff is shifting every couple of months, and I don't know the exact answer.
I know, 600 is peak
Right.
on it. More likely you're going to get, what, in the 500 maybe range.
It all depends upon the program and how it fits in the secondary cache and stuff like
Everything
that.
else. So, I mean, there's different.
And we'll talk a little bit about peak versus theoretical peak versus peak payload or payload bandwidth.
I mean, there's a lot of things though that what you get, but they still should be able to get 75% of that.
And keep in mind, we're kind of jumping ahead here, but with you could have 2 chips at the same clock rate with completely different megaflop performance. For example, a 195 megahertz R10K can beat out a Pentium 3 at 500 megahertz. Code 2 will take twice as long on a chip that's twice the clock speed, because it's not designed for floating point. And you may not have an instruction issued every clock period. So the clock period is not the only relevant issue. Now if I'm taking 2 MIPS chips and I double the clock, then I'm actually getting pretty close to clock speedups with some of my codes if they're a CPU mount. So for code 2, if I go from 200 megahertz to 400 megahertz, I get almost a double, cut in half in performance because it's pure CPU.
Do you see anything on the R12K specs yet? You know, that's the best held secret we've got.
What about it?
What the M-flop rating is on the R12? I haven't seen nothing.
And R14 they're pushing right now at 550 megahertz, pushing just over a gig.
They are getting a gig clock off of it?
Yeah. They're MRing it in the next week or so.
Yeah.
And that's at 550 megahertz R14.
Yeah, I'm guessing R12 must be running about 800, but that's a guess.
Yeah, it's a guess. But that's what I said earlier. I looked up the technical specifications, and that's why I'm trying to avoid this chapter. When I started off, it said here, don't distribute, the numbers here are going to be old by the time it's published. Okay? So I'm trying to avoid that subject right now, because there's so much flavor going on out there. But the main thing in this chapter was an HI and V, and I'm assuming everybody's used HI and V, so I can figure out how many CPUs I've got, what the clock rate is, what the in-house processor or the module design is, IP27 being the Origin 2000, okay, IP33 is the Origin 3000. And then for each of these, even at a clock rate of 190, the secondary cache may not be clocking at the same rate. So you got to be a little careful of that. These are 1 megabyte caches for some reason. These were the older boards in this particular system. Then I see in this example my main memory was 512 megabytes. Don't really care about the rest of that. And then I could go off and count my disk drives. In this case I just have one SCSI disk, S0D1. I just want to go on though. So if I were to look at my CPU capacity, my CPU services, it'd be the number of CPUs times the time in the interval. So we're going to go to accounting data later in the week. If I'm looking at accounting data for a day, there's 24 hours in a day times the number of CPUs on the system. That's the capacity that I can deliver. So a data center manager at the end of the month will say, where did all my CPU hours go to? 1,440 minutes to a day times the number of days. And then they go to accounting data and say, I only see 15 days worth of work here. What happened to the other 15 days? The machine could have been idle, or programs may still be running. We'll talk about some of those sorts of things. So my CPU capacity is the number of CPUs times the time interval. My memory is basically memory size dependent. We're going to talk about something called a memory integral. Every time I go through a minor clock interrupt, every 10 milliseconds, I add the number of pages to the process into a bucket. So it's an accumulator. So every 10 milliseconds I say, this thing's 10 pages in size. So I go 10 pages, 10 pages, 10 pages, 10 pages. And that thing has been around for a second, that would have occurred 10 times. And that's my memory integral. So my memory integral is basically how much memory was used for every second that I was in the system. It's usually marked in K-core minutes or something like that. And basically, again, we're simply adding the number of pages on each minor clock cycle into a total sum. For my I/O capacity, and my I/O bandwidth is completely file system dependent and device dependent. Okay. And you have to be careful about the devices you choose. For example, we'll come back to this as well. Had a customer in Germany, bought a fiber channel, was rated at 100 megabytes per second. They ran their application, only got 40 megabytes per second, and refused to pay for the drive. Now, why did they not get 100 megabytes per second? They were not matching the request size the RAID device was designed for. Remember that 64K byte is a hole-friendly number? If I don't match, if I don't fill those fire buckets up all the way, I'm going to waste bandwidth. So this thing was designed for 64K byte transfers, and they were doing 4K byte transfers, and they were not getting the bandwidth because the request size was not large enough to break across all the drives in parallel. Once we stressed it with the appropriate record size or request size, they got the 100 megabyte as specified. Now there's a command to actually stress it called disk perf. So with disk perf, I can specify various options like whether I want to go through cache or bypass it. But a couple of the key ones in here is my sizes. Disk perf to create a test file specified to a particular size. And right here is my request size. So here's the one that they did not stress appropriately. So it was set for 64 kbyte, and here the default was 16 kbyte. Okay? So when you do -R, you can specify what's the minimum request size you want, and then the -M says what's my maximum request size. So I could stress my disk drive from 4K up to 64 meg or something like that, and then find out what request size is that device, disk drive, or file system designed for. Okay? So if I have a 64 kbyte bucket and I fill it up with 32 kbyte of data, I'm wasting half the capability there. I'm not filling the bucket up all the way. So I'm doing all this handshakes and not getting any work done. A lot of times when you stress these file systems, you can actually see a sawtooth pattern where these are 16, 32, 64, 128, 256. They're whole friendly powers of two numbers. But maybe I've got an application that's doing 48 kbyte transfers. Now it's going to fill up a 32 kbyte bucket, and then another 16. It's going to waste half the fire bucket. Or if I go to 64, again at 48, it's only filling up 3/4 of the bucket. I'm wasting 25% of my bandwidth. So I could actually have this down 25% from what my peak was. Okay. So file systems are designed for a particular type of I/O request. And that's one thing you need to know. Got a case study. Guy calls in and says, taking 20 minutes for an LS to occur. They were running a database engine called Retrievalware. They were doing 4 kbyte transfers. And the device that they had put all this stuff into was RAID 5. And if you go to the marketing slides about the disk drives, they'll usually tag the device as saying this one's good for video or this one's good for database. What they mean is the database ones are good for small I/O, and the RAID other devices are designed for video. And here they sold the drive based upon capacity. It was an EMC drive designed for large sequential I/Os, and the application was not doing that. So they used TAR. Figured out, oh, these are 4 kbyte transfers. Talked to the developer. No, we can't up the request size because the data that we're databasing is in that record size. So if we can't up the request size, the only thing we can do then is drop the geometry of the disk drive down to match it. So basically somebody would go out to the site and use your RAID GUI command to unbind your logical units and then rebind them to 2 wide instead of 4 or 8 wide. So they basically narrowed the strike width down. And then they got separate individual drives within that cabinet, and then they could overlap and interleave their I/O to the separate drives. Okay? So what I'm trying to say is your file system is so dependent upon how you striped and how you built your file system. You really have to measure it. Okay? And every time you make a change, you should remeasure it. And that's what that disk perf command is there for, to stress your file system and give you some measurements. Okay? So this customer said, I'm not getting 100 megabyte. Then run disk perf and show, well, when you're doing a 64 kbyte transfer instead of 4 kbyte transfer, you get the full 100 megabyte. Because that's what it's optimized for. And that's why you need to profile and use things like PAR to figure out what these request sizes are like. Okay. I'm going to come back to that comment. So real briefly, the R10K, 12K, and 14K are the 64-bit chips that we have within SGI. Risk, I'm a Cray person, really invented by Seymour Cray. Risk means that we have discrete logic to decode our instructions. I used to work on microcode machines like Pentium chips. Every time they decode an instruction, they go to a memory stream that causes up a stream of bits to get read out of memory that toggles the chips, toggles the gates within the computer. So microcode machines are slower in general because there's a lot of space devoted to the memory for this stuff, and I have to go through the process of reading this memory to cause all my gates within the microprocessor to switch. Crays, for example, were always RISC. type architectures, discrete logic to decode the instructions. There's a lot of similarities here between this and Craze. So it's a MIPS 4 instruction set and something called superscalar. What does superscalar mean? We can have more than one instruction in the process of executing at a time. And I don't remember the numbers off the top of my head, but the R12 and the R14 have upped the numbers.
5 on R10, 8 on...
That's per functional unit. It's a little bit higher than that, actually. You actually will see this, break it into 4 different queues, and then each queue has a certain number of instructions that are in the process of being decoded. But superscalar means I've got more than one instruction in the process of being executed at the same time. And some instructions take more than one clock period. Okay? And we can do out-of-order instruction. So when I'm packing this instruction queue, I can say, oh, this instruction only takes 1 clock period. And there's an empty clock period here where I can pack it in. So when they're building this instruction queue, they're able to shuffle the instructions in the queue to better time the things. In fact, in old Cray days, we'd have to pull out the timing charts and figure out a loop and say, how can I best line these instructions to pack it as tightly as possible, to overlap my instructions being decoded. Now this chip has 2 integer arithmetic units to do adds and subtracts, or and operations, logical operations, on my integer data. Then we've got memory load and store, addressing capability. Then we've got 2 floating point functional units, a floating add and a floating multiply. Now why is floating point so important to us? Why not just scalar instructions, or integer instructions, I should say? What does floating point give us?
Bigger numbers.
A wider range of numbers.
Okay.
I can represent a wider range of numbers because floating point allows me to put them into scientific notation. So in the scientific world, we go to megaflops, and it matters to us because we're representing scientific problems, and we need a wide range of numbers to be able to be using. Otherwise, we truncate numbers and clip and all that kind of problem. If I'm on a database engine, I probably don't care about floating point operations, or a web server. I don't care about megaflops because my web server is doing integer operations. In fact, most of it's probably I/O. This whole battle between Pentium and Alpha chips in advanced machine device, AMD type chips. The Alpha, or I should say the Athlon, is more popular these days in the Intel market, not necessarily because of the clock rate being a little bit faster, but because there's more emphasis on the floating point capability. So in the microprocessor, they put more design effort in the floating point number crunching, which is what gaming people need, because all your 3D visualization is ray tracing, and there's a lot of geometry there, and that's why they need floating point capability. Okay. The Pentium 3 is not designed for scientific calculations. Most of the real estate on the Pentium 3 is designed for image manipulation, web browsing. You've got what are called SIMD units, single instruction, multiple data, which are primarily designed to do image manipulation. So the Athlon's better for gaming and floating point capability, where the Pentium 3 is better for web browsing and doing multimedia. They have different advantages to them. Okay. But anyways, floating point is more commonly in the scientific market, the compute server market, and that's what we care about when we're benchmarking things. But in the database market or web market, it would more likely be just integer instructions, MIPS rather than megaflops. Now this chip, the R10, 12, and 14 have 32 hardware counters in them. So what we're doing is saying every time I decode an instruction, increment a counter. So at the end of 6 minutes, I can say how many branches did I do? How many memory loads did I do? How many floating point operations have I done? And by the way, the Pentium chips also have hardware counters. So I can get into those counters on Pentium platforms as well. Then we've got on this particular chip a 32K byte instruction and a 32K byte data primary cache that's on chip. It's called level 1 cache. Some of our new Intel products are coming out with a level 2 cache that's on chip now, and we're now getting into level 3 caches that are on board. That's more for the Linux market, not the MIPS market right now. And that all depends upon the Intel chip that we're starting with. If it's got level 2 cache on chip, then we're, in some of our platforms now, putting a level 3 cache out there. And that's also occurring in some of the other vendor markets as well. Now, whenever I manipulate data in a cache, I have a geometry question and that says a cache line is 32 bytes or 64 bytes at a time. I cannot manipulate 1 byte at a time. When I change a byte, I have to change the entire line of data. Okay? So if I have an index counter that says how many times did I go through the loop, and then right after it is the variable for pi that I've hard-coded in there, maybe I'm multiplying every number by pi or something. Okay? So in that example, the right index counter is constantly changing as I increment it. And on the same cache line, right next to it then is pi, as defined as a constant within the program. So every time I rewrite I have to reload pi. Now every CPU out there that's trying to get to pi has to wait for that cache line to get reloaded. So 32 bytes or 64 bytes is the smallest granularity that I can manipulate things. Now in that example of what's called false cache sharing, where I have read and write variables on the same cache line, there are compiler directives to say push this variable onto the next cache line. I waste cache line, but now they're not interdependent. So now my write variable is only writes, and then pi is on the next cache line, and I can read it without waiting for the write to be finished. Okay, we'll talk about false cache sharing Wednesday morning, more than likely. So the cache line size is the smallest manipulation I can do. It's not a byte machine, this is actually a page machine with cache line geometry questions. Now these are a little bit older. 180 megahertz was our first platforms with 1 megabyte caches. 195 is 4 megabyte. There's quite a bit of newer opportunities out there depending upon what board and what product line. But right now we do have 8 megabyte caches running on the Origin 3000. And right now it's still, I think, 128 bytes for secondary cache in my cache line. So if I'm writing into secondary cache, all 128 bytes would have to get refreshed or reloaded.
You got 8s on the 400 megahertz 31s.
Yeah, 8 megabyte caches.
On the R2000, or on the Origin 2000.
Right.
Yeah, 400 megahertz.
So there are some Origin 2000 that are carrying the 8 megabyte boards as well. And again, that's why I'm trying to get rid of this chapter, because this stuff changes quicker than I'd have classes. So this is real old too, just comparing some of the different platforms. And like I say, I'm just, those pulled out of our marketing slides, and I'm not going through them. I'm trying to get rid of this stuff. This page I do want to keep basically listing the newer products. The IP33 is the Origin 3000. So it's describing what the module type is. But for example, I could have, earlier today we saw IP22 that was on Gull or IRIX, but I couldn't tell whether it was an Indigo, Indy, or a Challenge. I could tell what the module type was, but not the chassis type. Okay. Sometimes with HID you can tell the chassis type by some of the other comments about peripherals that are attached and stuff.
Graphics.
Yeah. Tell you about a variety of things. But HID by default doesn't give you a good idea of what the actual chassis type is. And IP17 isn't supported anymore with 6.5 IRIX. Okay. So this is just showing our architecture. This is what's called the SIS Bus going off to the module. There's going to actually be a hub chip, or in the 3000 a bedrock chip off of here. And then this shaded in area is my functional units for my microprocessor. And then off die, but on board, we have a dedicated bus to my secondary cache. This may have a different clock than my CPU. And this is showing it's 128 data wide. By the way, especially for Cray people, an SGI word is 32 bits. A Cray word was 64 bits. So they will refer to this as a quad word, which is 4 32-bit packets. So you're going to see some references to quad words moved to secondary cache. And that's what they mean, is 128 bits wide. Plus 9 for error correction, 26 for protocol to control the secondary cache. Okay. Then out of all this, then here's my instruction cache and my data cache, and they've got description about their size, and what's called set associative, which says how many references can be coming out of the secondary cache at the same time. There's some good books to describe that, but it's not relevant in this class. But Kurt Schimmel from SGI wrote a book on Unix and modern system architectures that gets into the history of cache, Snoop cache, and CC NUMA and stuff like that. Now coming on to this instruction cache, when we put the instructions into the cache, we partially decode the instruction right away. So when it goes into the instruction cache, we know which functional unit it's a part of. There are 3 functional units: floating point, integer, memory addressing, and branches. Okay. So when I'm coming out of secondary cache, I already know which queue to put it on. And this is where you can get into, again, multiple queues with multiple instructions in each queue. So the newer chips, we have this address queue has a lot more instructions on it, and the fact that I've got 4 queues allows me to have 4 pipes of instructions going on at the same time, as long as they're different areas of the hardware. So when I read my instruction out of the instruction cache, I already know which queue it's going to go on to. The instruction decode then figures out my registers and starts causing the gates to switch in my microprocessor. So my instructions go onto these queues, and then for each of these we've got our registers to hold my data, and then the functional units that are attached to them. What about a TLB buffer? Anybody know what that is? Everyone says the standard answer: translation look-aside buffer. Pentium chips have them too. The TLB buffer is a cache keeping track of the physical location in memory where a virtual address is contained. IRIX is a virtual memory system. As far as the program is concerned, every address is virtual. And then when I actually allocate the page, the operating system will figure out where I physically place the page and then put that address into the page table. If I go for an address, I look at my TLB buffer first. If it's not there, then I ask the operating system, please find this page for me. It goes to the page table, gets the physical address, and puts it into the TLB buffer. So the TLB buffer simply maps virtual addresses to physical addresses. TLB misses are normal. You have to have TLB misses on this type of machine. All your virtual memory machines are TLB based. Pentium chips actually have 2 TLB buffers, one for data, one for instructions. The size of that TLB buffer will depend upon the machine. But right now we're typically at 128 addresses that we can hold in the TLB buffer. And one of them is the kernel itself. It's called hardwiring. So every time I get an interrupt, one TLB buffer address is always the interrupt handler at entry point into the kernel. Okay. So I don't have to go ask the kernel, where are you? I've always got the kernel in there. Now we're going to talk about large page sizes and TLB misses tomorrow afternoon. But it's normal to have TLB misses. What you don't want to have happen is have all your work be TLB misses. So if I looked at code 4 and saw it was 365 seconds of CPU service time, and then I ran perfx to look at the hardware counters, and the hardware counter said it was all TLB misses, then I might start considering larger page sizes, for example. But I'm just trying to say TLB misses are normal as long as they don't dominate your service time. That's pretty much everything we had here. We also had a branch unit. One of the biggest difference between the R10 and the R12 case, they added more memory for branch history. So the branch is keeping track of every branch I did and doing what's called predictive branching. So if I'm in an enter to do loop, I'm taking the do loop a long time, and I'm going to predict that the next do is probably going to jump me back to the beginning of the loop. So if I'm running for a day, crunching that data through that do loop, predictive branching helps me. But maybe I'm jumping all over the place, what we call spaghetti code. You know, where you're jumping 15 routines deep and not doing anything. In those situations, the branch history is not going to help you because there's no prediction. And I've always felt database engines, and I would expect Java also to be a spaghetti code type of thing, just because of the paradigm of the way they're programmed, the way they nest things so much. But the R12K added more memory so we could keep track of more of our branch history. That's one other thing I should probably explain now. My hardware counters, I have 2 types of counters: issued and graduated. Issued says I've started the instruction. It's in the queue. So if I decoded something to say, do this addition, add pi to this number, okay, it's going to get into the queue. But I'm speculating as to whether it's actually going to occur yet. If suddenly I hit the branch and the branch says you've done all your loops, branch out, that speculation was incorrect. Okay? So you have issued that says when they started and then graduated when they finished. And you could have instructions that issue but never graduate. Now there's also the possibility of having issued higher than graduated, but that's a counter problem within the chip because it's not counting prefetch operations and a few other instructions that are overlapped. So we'll come back to that issue a little bit later. Anyway, try to wrap this up. So we're taking these two microprocessors and putting them onto a node board. The latest node boards are using 4 chips, 4 R12 or R14Ks with 1 to 8 megabyte secondary cache on them. They're dedicated. Nobody else is sharing that hardware path. But they are sharing what's called the SIS bus. And the SIS bus feeds into what's called the hub chip on the Origin 2000 or the bedrock chip on the Origin 3000. The hub and the bedrock are essentially the same. They've been adjusted, clocks have been boosted. They're not electrically compatible, but they're conceptually identical. Okay, there's just been adjustments to protocol lines and stuff like that. Now that hub chip then feeds my SIS bus to either my local memory or off to another node board through a router or off to my I/O subsystem. Okay, so it's a multiplex switch with several I/O paths going through it. Now that's the one thing nice about the Origin versus the older challenges in bus-based systems. As I add more and more hardware to the Origin, I'm also getting more and more hardware paths that are separate from each other. So I'm not bottlenecking on my bus anymore. As I add more and more node boards, I get more and more fan out, giving me more and more bandwidth as I grow my system. Whereas bus-based systems, you saturate the bus, and no matter how much more hardware you add, you can't go past the capacity of the bus that you have. By the way, what's the disadvantage of putting 4 CPUs on the Origin 3000 out there? What's the disadvantage?
Saturate the bus faster.
The SIS bus itself, if I've got a memory-intensive application where I'm always going to memory to get my data, now I've got 4 CPUs sucking data into that SIS bus, and I can saturate that SIS bus quicker. So with the Origin 3000, you do have the option of specifying how many CPUs you want on your node boards. So I may be getting node boards with 1 CPU fully loaded with memory because I don't need the other CPUs. Or maybe I don't want the other CPUs for the memory contention or something. So you do have that option. Eventually, when you're system tuning, there's always a bottleneck there, and eventually it comes down to your bottlenecking on the SIS bus trying to get to your data. Anyway, maybe I should mention this as well. What's directory memory for? Unique to SGI.
To put the directories in.
It's how I keep track of my cache coherency. That's correct.
Ah.
So in my directory memory, there is an address representing every physical memory address. In that directory memory, then, is a count or a pointer to the CPU number that is using that memory address. So if I modify a memory address with a write, I'm going to use the directory memory to figure out what other CPUs have this memory loaded into their secondary cache, and then I will send them an intervention invalidation signal to say, reload your cache lines. So we don't really care about it in detail, but the directory memory figures out what CPUs are sharing that cache line, and then I'm going to send off interventions invalidations to those CPUs to say, reload your cache line because I just modified it. Now before we had that, standard chips were using what's called snoop cache. And with snoop cache, you're just sitting there looking at the memory addresses and saying, oh, that memory address is mine. I better resync my memory. But that has scalability problems. Not that this doesn't either. They are experiencing scalability problems when they get past 256 CPUs and stuff with the directory memory concept. So everything has its limit. But it's hardware support for cache coherency rather than software support like snoop cache is. We then put those node boards into what's called a topology, and the topology used for the origin is called a hypercube. I worked on Cray T3Es, that was something called a Torus 3D. It was kind of like a hypercube, but it had additional loop-de-loops in there, so that you had multiple paths to it. So with the origin 3000, it's the same concept. The only difference is we get 4 CPUs per node board rather than 2. So each one of these points is indicating a node board. We then connect everything together with routers so that any CPU can get to any memory or any other node board on the system. So it's a common shared memory across all the CPUs. Some are locally attached and some are remotely attached. If I have to go across the hypercube to get my data, it may take longer to get it. Okay. Once I go, by the way, at 32 CPUs, I can actually connect some open ports with express links to give me additional paths through the system. The customer pays extra for that. But when I go past 32 CPUs, those open ports basically connect to another hypercube. And then when you go past 64, you get into what was called the meta router. If you've ever looked at the origin, the large systems have that center black thing with the LCD display. That's usually where your meta routers are. So in this example, I've now taken 4 hypercubes and connected them together with one meta router. It's giving me a 128. We are running up to 512 CPU systems. NASA Ames is doing that. And the intent is to eventually, I think, still planning on stopping at 1024 CPUs in a system, in a single system image. So if I go to 256, I actually have 2 meta routers in there, and beyond that, I got 3 meta routers in there. Okay. Anybody know the command to show me what the topology looks like? Called O-view. I'm just going to bring up O-view here. And this is a 16 CPU system, so I won't have a cube. Okay. So there's my topology. Each of these is a node board. 2 CPUs, 2 CPUs, 2 CPUs. I've got 4 routers in my system. 16 CPU system. Now O-view will also give me SAR-U data. So when I drive up my workload, I'll be able to see the CPUs go busy and stuff like that. So it's able to give me a picture of the topology and also show me how busy things are in that topology. In fact, I just saw a router go a little bit busy there. It flashed for a second from a light blue to a little bit stronger blue. What I'm going to do here is try to fire up a workload. Try this again. So I'm trying to get a larger load going on the system, and now I can start to see I've got a couple of CPUs going busy here. There was some system time going on here. The routers are starting to get a little bit busy. I got 1, 2, 3, 4 CPUs that are busy right now. But I haven't really loaded the system down yet. And what I was trying to see was these Tinker Toy sticks will actually change color to see the traffic, the direction that my data is moving within the topology of the system. Okay. Now this is PCP, and with these GUIs, if you place your cursor over the item you're interested in, it will show you what the metric is up on top. So this is my router's receive utilization. Okay. So I place it there. We got something that went yellow. The hotter the color, the busier it is. Okay. Now what would be nice is if I could click on that CPU and then actually see what processes were running on that CPU. You don't really get that immediate correlation here. You can figure out with PS what CPU it's on, but by the time you look, it may be on a different CPU, so that's kind of hard. Okay. I'll try to find a larger system a little bit later. I do like to get on 128 CPU systems and abuse them like 2 CPU systems. People don't like me because I beat up on their computers. I log in and do everything I can to create problems. Just real quickly, this is just describing some of our performance metrics. Bandwidth is basically the data rate transfer, data moved in a per second rate. Peak bandwidth is theoretical. This is what Warren and I were talking about. Peak bandwidth is usually the bus width, number of bytes in the bus width times the clock rate. So for example, it was a 128 byte bus to the secondary cache. As I up the clock, my bandwidth to that particular thing is going to get better. But not everything on the bus is data movement. That SIS bus, not only do we have data going across it, but every data item has the address at the beginning and end of the data item. So I may have a theoretical peak, but 25% of it might be used for a handshake protocol and non-data payload type of information. So the peak is theoretical, and the benchmarkers like to quote it and everything. People that haven't built the machine yet like to quote it, but it's not real world. So peak payload bandwidth, or what I like to prefer to call sustained bandwidth, is more what you get in real world. Warren and I were talking about this in megaflop performance. I'm just being a generic concept of theoretical is usually clock rate and what you can actually get based upon the hardware design, and then sustained is what you in reality truly get when you subtract all the overhead that may be involved in handshakes and arbitrating the bus and things like that. So in the SIS bus, there was a slide a couple slides ago that gave you bandwidth on the bus. It was lower than marketing numbers because marketing numbers were based upon clock rate times bus width. But there's actually, for every word that goes across that bus, there's an address at the beginning and the end of the word. And that takes about 20% of your bandwidth away. The other end of the spectrum is latency. Latency is how long it takes to get to something. These are two different ends of the spectrum. How many people listen to music? You got bass frequencies, you got high-end frequencies. The same thing is true here. Latency and bandwidth are two different ends of the spectrum. For example, in the database market, we want latency. If I've got online transaction processing, how long it takes to get to that credit card transaction matters to me. When I order disk drives, we were talking about this earlier. EMC drive, the marketing slide will say this one's good for video market, this one's good for the database market. What they're saying is this one is designed for bandwidth and this one is designed for latency. Okay, I'm going to come back to that story. In memory, total memory bandwidth is adding all the memory systems. We're going to talk a little bit about this, but I got two options of placing my data in the system. It's a node board topology, so I could keep all my data on my node board. That's going to be the fastest latency to get to the data. But there's only one memory port into that node board. If I want bandwidth, I can spread my data across all the memory node boards. And now I've got multiple memory ports feeding me data at the same time. So this is another example where latency and bandwidth are opposite ends of the spectrum. So when I'm placing my data close to my memory, I'm giving myself latency, but I'm losing bandwidth. When I place it round robin across all my nodes, I'm able to increase my bandwidth, but reduce my latency. Okay? So latency is how long it takes to get to something, and bandwidth is how long it takes to move it. There's also bisection bandwidth, which is basically for topologies, what's the worst case scenario. If I take my topology and cut it in half, I have to go in from the farthest CPU's node board into my CPU. What's the worst case scenario? So bisection bandwidth is in topology-based systems, which does include networks too. When you talk about Beowulf cluster or clustering with network interfaces, that's a topology issue too. And when they talk about bisection bandwidth, they're measuring it across the network interfaces. The routers are really internal network interfaces. We usually used to refer to them as internal interconnects. So, I just want to try to wrap up here. This is a virtual memory machine, not a real memory machine. We can have programs larger than physical memory. You could never do that on a Cray. Crays had to have as much memory as the program. In fact, with a virtual memory machine, you can have memory that isn't really there, such as virtual swap. Okay, now IRIX has virtual swap, but Linux does not yet. By the way, it's distributed shared memory, which means my memory is distributed with my CPUs tightly coupled to the CPU. but shared across all the CPUs. And memory is not necessarily contiguous. I can populate my memory boards, my node boards differently. Now most sites will fully populate node 0 because there's a lot of kernel stuff that goes on in node 0. Okay? So if you are going to populate differently, node 0 is the one they usually put the most memory on because your process table is in there and stuff like that. So each node board could be populated differently. OSView, HIV, a couple of commands give you the size of memory on a per node basis. And by default, these are old again probably, but 8 banks with various sizes, 32, 64, 256, SDRAM DIMMs. The newer boards, the newer O2000 scoring higher. Now, older systems were what were called uniform memory access. This is your standard central memory system. This is your standard desktop at home with a compact or whatever it is that you got. I guess I should say Dell with this compact. So CPU access is any memory in the same time. It's a central memory concept. It's simple. We don't have to worry about placing our data. And most of the current SMPs are cache coherent. What does SMP mean? Symmetric multiprocessor. Now what does that mean? It's a multi-CPU system where the CPUs can be operating in the kernel at the same time. Some of us old-timers here, Unicos 5.0 was a single-threaded kernel. And I get out to a site and be 80% system time, and all of that was sitting there waiting for another CPU to come out of the kernel so that I could go in and do things. So what do SMP systems have to prevent multiple CPUs from stepping on each other? Locks. Okay? So older Unixes had one lock. I go into the kernel, I set a lock. When I'm done with the kernel, I release the lock. And that caused high system time. And all that time was spinning, waiting for somebody to get out of the kernel. We didn't want the other CPU in the kernel because maybe they're both trying to do I.O. And we do not want two CPUs changing I.O. tables at the same time. So now we have large sets of locks. In fact, I think IRIX is better than Unicos in its lock granularity. So you can get much lower system time on IRIX than you can on Unicos. Unicos has about 150 locks. IRIX has over 1,000 locks. I've documented all these locks. But why do I care? How do I know what lock the program is waiting on? PS-L, and over on the right are WCanfield. So the WCanfield is indicating the handler for the lock that I'm spinning on. If it's a dash, that says I'm not waiting on any lock. In this case, I've got a CPU number, so therefore I am connected to a CPU running. If it were a dash and an asterisk there, then I was runnable, but the CPU was busy, so I'm sitting there waiting on a CPU. Or I've got a lock that I'm waiting on. Question?
There's a way of pulling that lock out too, but I don't.
That's where we're going.
Okay.
I was trying to let you set me up first.
All right.
Now for me, that means nothing to me. 204 TB8P8, that's an address. Doesn't mean anything to me. But if I have a name for the lock, it will tell me quite a bit. Linux, for example, by default has lock names turned on. On a Linux system, when you do PS-L, you can see the name of the lock there. So if you're taking notes, here's how I turn on lock names. And then tomorrow morning, we'll see them actually happen with a reboot. This is also off of my web pages and stuff like that, but I'm going to go into var sysgen system. Okay, we're going to be back in this directory a couple other times too. var sysgen system, a file called irix.sm. And if I were out at site, I'd have this turned on all the time. It's not a performance impact. And I don't know why they have it off by default except historical behavior. Okay. So var sysgen system, irix.sm, and in there is a field called ksync. Now with the newer kernels, I can actually get statistics on how many times the locks are being hit, how long they're being held and stuff. We won't have time probably to try that, but that's really for developers. It's not a production mode type of thing. It's just for developers to adjust their lock granularity. Now if I'm on a single CPU system, I can say no locks. When you order Linux, Linux is built as a single CPU system. Well, you can build it as an SMP system. So there's actually a separate build compilation process to say turn on SMP capability for multi-CPU systems. Okay, so if I'm on a single CPU system, I can just say no locks. The default is just called hard locks, and then we can get statistics with debug code for developers. Now that's not the field I wanted. Here's the field that I wanted. K-sync, the default, I've got it, just K-sync is the default. And that's what I'm running right now. I can also switch it to what's called meter, which is for debugging by developers. We don't really care about that here. But the one I want is K-sync named. So, I have to actually go down to the field, and there it is, K-sync, and I'm going to change it to K-sync underscore named. Now it will require an auto config and a reboot to have this take effect. But I find this extremely useful, and I advise people that are working on large systems to have this turned on by default. It's not a measurable performance impact. PS is the only thing that uses the code that does this. You know, so if you're running PS every second, the PS may accumulate a lot more CPU time. But it's not going to increase your system time. It's not going to increase your user time. It's not going to impact your wall clock time unless it's a program that's running PS. So if you want to try this on your workstation before we leave today, feel free. You do have root on your workstation. So I change it from K-sync to K-sync named. Let's see if I have write permission. Yes, I do. And now I do my auto config. Of course, I should have done that before anything, just to make sure I can build a clean kernel before I change anything. You know, before you start changing. I've had a couple of cases where I sit down at the machine and it won't build because of NFS libraries that were out of sync or something like that. And I always use VF. VF is verbose and F says force it. I don't care what the kernel you've got there right now is, I definitely want to rebuild it. And then after a reboot, that PS will show me lock names instead of lock addresses. Now I'm going to come back to this later, but going off to my web page, I've documented all the locks on the system. So it's in this HTML file, and I'll show you this when we come back to locks later. But I'm going into my raw HTML file, and the chapter is on CPU utilization, step 16 here. And in here I talk about locks. So I describe what the locks are. We have two types of locks, spin locks and sleep locks. With the spin lock, I use the CPU and hold it, and that will show up as system time. With sleep locks, I get put to sleep until the event is done, like the sleep command itself, or I/O. So in this chapter, I then document, I've got some CPU utilization stuff, context switching. And then here is where I actually describe kernel locks, the names of the different routines that handle kernel locks in the kernel. And then for each of these subroutines, I've got the name of the lock that you should see with PS. I'm working on descriptions for the lock. Then I've got the actual subroutine name in the kernel that manipulates the lock, and the source module where you can find that lock. So if you're using cscope, which is our source browser, this is in the order that cscope would bring them up. So it's basically sorted by the source tree path alphabetical order. I don't want to alphabetize the lock names because I want to be able to figure out, oh, it's 20 down in cscope. So I can figure out, you know, how deep do I have to go with cscope before I find that particular lock name. So they're basically ordered in the order that they would pop up with cscope.
Can you unlock one's log, that, you know, the process log with waiting for that log?
I'm not sure what you're asking. with BS, we would then see the name of the lock that it was waiting on.
Right, there is a way that you can make the process to no wait for that.
No, the kernel may have to optimize the lock, or else you could rewrite your code such that you don't make a system call that hits the lock. But the programmer can't do much about the locks. That's the engineering kernel developer issues. Okay. So for example, there's an I/O lock every time I use buffer cache. If I'm bound on that lock all the time, I could bypass cache, do direct I/O, and never use that lock. Okay. But just backing away from it, I'm just interested in, if I know what lock it's waiting on, I know what subsystem. Is it an NFS lock? Is it an I/O lock? Is it a CPU lock? You know what I used to find on large crays? The run queue lock. So when I got into 32 CPU systems and larger, it was one run queue, and I'd have 28 CPUs idle, waiting for the run queue lock to get freed up so that I could look for work. Now IRIX has separate run queues. Every CPU has its own run queue, so I don't see that lock anymore. But once you identify the lock, you now know what is the contention, who is contending for that particular lock. And then if you know what functionality that lock has, a lot of them you have to look up. Okay, there's a lot of locks there, and that's why I documented them so that I can say, here's the lock name I see, go to this table and figure out what area is that. Is it a malloc? Is it memory growth? Is it process creation? And a variety of different locks. And I got over 1,000 of them. Okay. So anyway, that's what SMP systems are about. And we'll come back to locks later. Wrap up here. Ignore this chart, just showing some of the latency bandwidth specs. Don't really care about memory latency either. Here's the deal. NUMA architectures, you should not see NUMA because it is a cache-based machine. If you solve your cache problems, you will satisfy your data out of cache and you don't see NUMA. That's the purpose of cache. The purpose of cache is to hide memory latency. Okay? But if my program's bigger than secondary cache, then I've got problems because now I keep missing cache and having to go to memory to see it. So all tuning, you want to fix your cache issues first. And I'm going to talk about that tomorrow afternoon. So I'm just saying this is the latency to get to data, but if I satisfy it out of cache, I don't see the latency in the router hops or anything like that. I'll come back to buffers versus caches later. And this is just trying to show my I/O fan out where my hub from the node board goes to an expo. The expo is actually in the back panel of the Origin 2000. I'm not sure where it is in the 3000. Probably in the XIO brick, the X brick. And then that crossbow is basically another flavor of the hub chip or the router chip. The hub, the router, and the crossbow are all the same type of chip. They've just been adjusted for their particular purpose. And coming out of the crossbow, we may have one or two graphics boards, graphics heads. And then we've got these bridges, these XIO cards, that convert the crosstalk protocol that is SGI specific into PCI bus protocol. And that way we can put third-party vendor cards that are PCI compliant into our platform. Okay. So this is just trying to show some of the network interfaces, my Ethernet and my video, audio, workstation type stuff. I may have FIDI, SCSI, fiber channel, VME buses. IRIX, SGI vendors or users generally use VME buses for data acquisition devices. In older days, we may have had disk drives out there and stuff like that, but nowadays it's really data acquisition devices. How many people have watched hockey nowadays? And you get a little white spot that follows the hockey puck around. So they have a telemetry device in the hockey puck and then receivers in the auditorium. And then on an SGI equipment, they're feeding into the VME bus the data acquisition device to feed into their software. So they write their own program to take the data coming from that telemetry device, and the program has to have a device driver written to understand how to talk to the VME device. Okay, so that's usually where you're seeing VME buses, is data acquisition. If I'm tracking Star Wars Scud missiles coming down, I probably have a data acquisition device on a VME bus or something like that. Real-time markets, factory process control, those sorts of markets is where you're going to find BME buses used. I've never hit a compute server or a large system that's using BME buses. It's usually the real-time data acquisition, process control type markets. There is a manual out there. I don't want to care about it right now, but how to distribute your XIO boards. Basically, the concept is round robin them across your CPUs. And then this is just listing some of the different I/O cards. And I want to wrap up here. So, when I go for a disk, I want to get the disk characteristics. And it's getting hard with all the different flavors of disks out there. Even on my home PC, when I went out and bought a disk drive, I had several factors to consider about what drive I wanted, including price and reliability. Okay? So the first thing is my controller interface. We've got SCSI and we've got fiber channel. Fiber channel